Understanding key statistics concepts. By the end of this session, you will understand why the mean alone can be misleading and how dispersion helps, what descriptive statistics are and why we use them, how to calculate probabilities using Poisson and normal distributions, the difference between discrete and continuous probability distributions, when to use stratified sampling versus cluster sampling, the magic of the central limit theorem, CLT, how to measure the relationship between two variables using covariance and correlation. Dispersion. Complements central tendency. Consider two classes have the same average exam score of 50 out of 100. Does that mean both classes performed identically?
Not
necessary.
ly.
We have two types of summary numbers. Measures of central tendency, mean, median, mode, tell you where the center of the data is. Measures of dispersion, range, variance, standard deviation, tell you how spread out the data is around that center. For example, dataset A, 50, 50, 50, 50, 50. Every student got exactly 50. The mean is 50. There is no variation, low. Dispersion. Dataset B, 10, 30, 50, 70, 90. The mean is also 50, but look at the spread. Some students got 10, some got 90. That is high dispersion. If you only report the mean, you would say both classes are identical, but that would be wrong. Class A is perfectly consistent. Class B is highly inconsistent. The mean alone does not show variability. The low dispersion diagram shows all data points clustered around 50. Imagine a tight group. The high dispersion diagram shows points far apart, from 10 all the way to 90. Key takeaway. Measures of dispersion complement central tendency, where data values are distributed around the average. Without dispersion, the mean can be completely misleading. Always report both. Descriptive statistics, summarizing data. Imagine you have a list of 10,000 exam scores. Looking at all those numbers individually is impossible. Descriptive statistics gives you a summary, a few numbers and a simple graph that tell you everything important about the data. Descriptive statistics are methods to summarize, organize, and present data meaningfully. They include numerical measures and graphical tools. Components are 1. Measures of central tendency, mean, median, mode. 2. Measures of dispersion, range, variance, standard deviation. 3. Graphical tools, bar charts, histograms, pie charts, etc. Example dataset. Marks of 5 students, 40, 45, 50, 55, 60. Graphical representation. Simple bar chart. We can draw a bar where the height shows how many students got each mark. For example, 1 student got 40, 2 got 45, 3 got 50, etc. This visual makes patterns obvious. Significance of descriptive statistics. Simplifies large datasets. Instead of 10,000 numbers, you say mean equals 72%. Identifies patterns and trends. You can see if most students passed or failed. Enables comparison, compare two classes, 2 years, or 2 products easily. Supports decision-making. A manager uses average sales and variation to decide on bonuses or training. Use in data analysis. Mean, average performance. Median, typical value. Useful when there are outliers like very high incomes. Standard deviation. How much variation exists in performance? So, descriptive statistics turns raw data into actionable information. Poisson distribution, counting events over time. If a customer care center gets an average of 3 calls per minute, what is the probability of getting exactly 2 calls in a given minute? Given average number of calls per minute, lambda equals 3. Refer Poisson distribution formula as given in the slide. In part A, exactly 2 calls, k equals 2, so about 22.4% chance. In part B, at most 4 calls, x less than or equal to 4, at most 4 means 0, 1, 2, 3, or 4 calls. We calculate each and add them. P0, P1, P2, P3, P4, and its sum are calculated as shown in the slide. Why do we use Poisson here? Because the scenario meets 4 conditions. 1. Events occur independently. One call does not affect the next. 2. Fixed time interval. We're looking at exactly 1 minute. 3. Known average rate. We know lambda equals 3 calls per minute. 4. Suitable for counting arrivals. Calls are countable events. Diagram idea. Imagine a timeline of 1 minute with marks showing when calls arrive. They are random but average 3 per minute. Poisson is very useful for call centers, traffic flow, number of emails per hour, etc. Normal distribution. The bell curve for heights. The normal distribution is the most famous probability distribution. It looks like a bell, hence bell curve. Many natural phenomena follow it: heights, weights, IQ scores, measurement errors. Given, heights of students in a college are normally distributed with mean mu equals 165 centimeters and standard deviation sigma equals 5 centimeters. Part I. Probability height is between 160 centimeters and 170 centimeters. We need to find P, and where XLU between 160 and 170. Z-score tells us how many standard deviations of value is from the mean. As per the formula, calculate Z. Now we use the standard normal table, Z-table. The table tells us that the area between Z equals -1 and Z equals +1 is 0.6826. That means about 68.26% of the data falls within 1 standard deviation of the mean. 68.26% probability. Interpretation. In any normal distribution, roughly 68% of values lie between mu, sigma, and mu plus sigma. Here, that range is 160 to 170 centimeters. Part 2. Why is height modeled by normal distribution? 1. Biological factors. Height is influenced by many small independent factors: genes, nutrition. The sum of many small effects tends to be normal, central limit theorem in action. 2. Symmetry. About as many people are above average height as below. 3. Empirical evidence. If you collect height data from a large population and plot it, you get a beautiful bell curve. 4. Statistical properties. Normal distribution has well-known rules, 68-95-99.7 rule, that make probability calculations easy. Importance in data analysis. We can estimate probabilities for height ranges, e.g., what percentage of students are above 180 centimeters. This is useful in health studies, designing furniture, ergonomics, and comparing populations. Diagram. Draw a bell curve. Mark the mean 165, then 160 and 170, and shade the area between them. That shaded area is 68.26% of the total area under the curve. Discrete versus continuous probability distributions. This is a fundamental distinction in statistics. It all comes down to, are you counting or measuring? Discrete probability distribution, used when the random variable takes countable values, usually whole numbers. Examples: number of students can't be 25.3, number of calls, number of defective items. Probability is assigned to each exact value. For example, P x equals 2 is meaningful, represented by probability mass function, PMF. Graph. Bar chart. There are gaps between bars because values are separate. Continuous probability distribution, used when the random variable can take any value within a range. Examples: height, 165.2 centimeters, 165.23 centimeters, etc. Weight, time. Probability of a single exact value is 0 because there are infinite possibilities. Instead, we calculate probability over an interval, e.g., between 160 and 170 centimeters, represented by probability density function, PDF. Graph. Smooth curve, no gaps. Comparison table as given in the slide. Why are some phenomena better modeled as continuous? Take height. You can measure it more and more precisely. 165 centimeters, 165.1 centimeters, 165.12 centimeters, 165.123 cm. There is no limit to the precision. If you tried to model height as discrete, only whole centimeters, you would lose information and get inaccurate results. Continuous distributions are natural for measurements. Discrete are natural for counts. Common mistake: saying p height equal 165 centimeters has a positive probability. In continuous distributions, that probability is 0. We always use intervals. Stratified versus cluster sampling. 2 ways to select a sample when you cannot survey an entire population, which is almost always. You take a sample. But how do you choose that sample? 2 popular methods are stratified sampling and cluster sampling. They are often confused, so let me clarify. Stratified sampling, how it works. Divide the population into strata, groups, based on a characteristic like age, gender, income. People within a stratum are similar to each other. Then take a random sample from each stratum and combine them. Analogy: to understand student opinions, divide by grade, 9th, 10th, 11th, 12th. Then randomly pick 10 students from each grade. Advantages: ensures representation of all groups. Higher accuracy and precision. Reduces sampling error. Disadvantages: need detailed population information to form strata. Complex and time-consuming. Cluster sampling, how it works. Divide the population into clusters, natural groups like schools, cities, city blocks. Ideally, each cluster is a mini representation of the whole population. Then randomly select a few entire clusters and survey everyone in them. Analogy: to survey a large city, divide it into 100 city blocks. Randomly pick 5 blocks and survey every house on those blocks. Advantages: cost-effective and easy to implement. Suitable for large geographical areas. Disadvantages: higher sampling error, less accurate. Possible cluster bias. The chosen clusters might not represent the whole. When to prefer each is given in the slide based on the reasons it would be selected. Key takeaway: stratified sampling improves accuracy. Cluster sampling reduces cost and effort. Your choice depends on your research goals and resources. Central Limit Theorem, CLT. The magic of statistics. The Central Limit Theorem, CLT, is arguably the most important theorem in statistics. It is the reason we can use normal distribution methods for almost any problem, even when the original data is not normal. Definition: if you take many random samples of size n greater than or equal to 30 from any population, even a skewed or weird-shaped one, the distribution of the sample means will be approximately normal. Moreover, the mean of all these sample means equals the population mean, mu, and the standard deviation of the sample means, called the standard error, equals sigma/square root n. Mathematical representation: mean of sampling distribution equals mu, standard error equals sigma/square root n. Assumptions of CLT. 1. Samples are randomly selected. 2. Observations are independent. 3. Sample size is sufficiently large, usually n greater than or equal to 30. 4. Population has a finite mean and variance. Why is CLT so significant? It allows use of normal distribution for inference, even if the population is not normal. It enables estimation of population parameters from a single sample. It forms the basis for confidence intervals and hypothesis testing, the core of inferential statistics. It simplifies analysis of non-normal populations. For example, suppose daily incomes in a city are skewed. Most people earn low income, few earn very high. Population mean mu equals 1,000 Indian rupees. Population standard deviation sigma equals 300 Indian rupees. You take one sample of n equals 36 workers and calculate the sample mean. Using CLT, the sampling distribution of the sample mean is approximately normal, even though incomes themselves are skewed. Standard error equals sigma/square root n equals 300/square root 36 equals 300/6 equals 50 Indian rupees. Now you can use normal distribution to say things like, the probability that the sample mean is within 100 Indian rupees of the true population mean is about 95%. Because 2 times standard error equals 100 Indian rupees. You can construct a confidence interval and perform hypothesis tests. Diagram depicts the skewed population distribution, long tail to the right, and next to it a normal distribution of sample means. That is the magic of CLT. Key point: CLT works for sample size n greater than or equal to 30. That is why in many statistics problems, we feel safe using normal approximations when n is large. We often want to know if two variables are related. For example, do students who score high in mathematics also score high in physics? Covariance and correlation give us the answer. Consider the given data. Calculate means x, y, which results 75. Part I. Covariance. Covariance measures the direction of the relationship, positive or negative. As per the formula, the covariance is calculated as 23. A positive covariance means a direct relationship. As x increases, y tends to increase. But covariance is not standardized. Its magnitude depends on units. So we need correlation. Part 2. Correlation coefficient. Our correlation measures both direction and strength. It ranges from -1 to +1. As per the formula, compute the correlation coefficient 0.88 approximately. Part 3. Comment on strength and direction. Direction: positive 0.88 greater than 0. As math marks increase, physics marks increase. Strength: 0.88 is close to +1, indicating a strong positive correlation. Interpretation: there is a strong positive linear relationship between mathematics and physics marks. Students who perform well in math are very likely to perform well in physics. This makes sense because both subjects require logical thinking and problem-solving skills. Correlation interpretation guide was given. Important to note that the correlation does not imply causation. Even though math and physics are strongly correlated, high math scores do not cause high physics scores. There may be a third factor like study habits or intelligence. Summary and key takeaways. The most important points from this session. 1. Measures of dispersion, range, variance, standard deviation complement measures of central tendency, mean, median, mode. 2. Descriptive statistics summarize data using averages, central tendency, and spreads, dispersion, plus graphs to understand data. 3. Poisson distribution models the number of events occurring in a fixed interval, given a known average rate. Use it for independent events. 4. Normal distribution is the bell curve. It is used for many natural phenomena, like heights. 5. Discrete distributions are for countable/measurable values, number of students. 6. Stratified sampling divides by similarity and samples from all groups, accurate but costly. Cluster sampling divides by proximity and samples entire groups, cheaper but less accurate. 7. Central limit theorem, CLT, says that for large samples n greater than or equal to 30, the distribution of sample means is approximately normal, regardless of the population shape. 8. Covariance tells the direction of a relationship, positive or negative. Correlation tells both direction and strength, not causation.